Alright, so what we're working on here. Is the definite interval. And this follows, this is right after that section we did, the first section we did. Was on Riemann sums, where we added up the area. We broke the area up into rectangles. And we added up the area. This follows that, and so. The Riemann sum version was k equals 1 to n. F of x k star. Delta x. And here we're going to, from length A to B. And the idea here, which feels weird to me. And we're gonna kind of gloss over like doing all the math for it, because it's not necessary. The rectangles don't need to be equal width. If. We say the limit. Of. Like the max. Delta xk. We send that to 0. So we like to, no matter how big the biggest rectangle is. We like wanna make that go to 0. Of this. That's one version of how they teach this topic, so if you hear that. I kind of like to think of the limit as n goes to infinity. So the number of rectangles goes to infinity. I like that approach better. In both cases, the width of the rectangle. Goes to 0. And so we end up capturing the whole area. Eliminating. The error from using an endpoint method. Or midpoint. We looked at doing it 3 ways. And this limit equals the integral. But now we have limits of integration. A and B are called the limits of integration. Where A is the lower limit or lower boundary. Boundary is an easier way to think of it, because it's like you're fencing off your property. And B is the upper limit. Upper boundary or upper bound, they often say, they just call it bound. And there's two scenarios for this. A and B. A. If f of x is greater than or equal to 0. For all x in AB. This represents area. And B, if not, it represents net area. Kind of like, if it's below, if there's a negative portion, you're subtracting that area.
The upside down A before the X is, what is it, all inclusive? What is it?
For all. I've used it a couple times before, but I do not mind reiterating it every time because it is something that's new and you've never seen it before. I don't use it that often. The more you see it, the more you get used to it. And at some point, it makes doing math easier. Which is why they did it. Mathematicians are lazy fucks. We do everything possible to minimize the amount of shit we have to write. Like doing the upside down A for all, we have something for there exists, because you do that with groups a lot. When you go to, if you go to like. Take like a real analysis course at university level, you do a lot of proofs. And you do a lot of there exists. And we abbreviate if and only if down to IFF, all just to save some characters you're writing. And anyone with a really long name knows how that goes. If your name's fucking Alexandria, going by Alex saves you fucking time in the long run. Time writing it out, time saying the name. Alright, onward. So we have a theorem that goes with this. If f is continuous over AB. Closed interval AB. Or. If f has. At most. A finite number of jump discontinuities. Then the definite interval exists. And f is integrable. Integrable. That's an awkward word to say. Integrable. Over AB. So like continuous functions. These are polynomials. Sine and cosine. E to the x. In fact, these are continuous everywhere. Natural log of x and like an even root of x. Is continuous on its domain. Like natural log of x, x has to be greater than 0. But this has to be, x has to be greater than or equal to 0. So like if you have those and you're only working with positive numbers. You have this and you have no problems integrating it. That's the first part, f is continuous over AB. But the second part is like we can have jump discontinuities. We could say f of x equals -1 if x is less than -2. We can say it equals 0 for -2 less than or equal to x less than or equal to 3. And we could say it's +2 for x greater than 3. So like if I graph this. The -2 to 3 is covering this. And then I have -1 to the left. And I have +2 to the right. We can integrate over this, like let's say. We go from a equals -4 to b equals 5. In fact, let's do it real quick. This is funny, like 5.5, they actually don't have you solving it, but we're gonna come and solve it. This is gonna bleed some of the stuff in 5.6 into it. And I'll tell you the name of the theorem later on, but we'll just use the property now. Yeah, I want you guys to be able to do that. So like we're gonna integrate from a to b of f of x. Dx. And this is integrate. From -4 to b, or -4 to 6, 5. Of f of x dx. This has different values over different regions. So what we can do is we can treat this as 3 areas. We can treat this as area 1. We can treat this area as area 2. And we can treat this area as area 3. So this allows us to, and this is one of the first properties that we're gonna have and show. This allows us to break this, treat this as adding up the 3 areas. We're gonna go from -4 to 2. And f of x equals -1 on that region. That should be a negative. And then we're gonna go from, oh wait, that should be -2. And then we're gonna go from -2 to +3. And f of x equals 0 on that region. And then we're gonna go from 3 to 5. And f of x equals +2 on that region. Does that make sense? That's how we could add area together, right? If we had a bunch of property next to each other, you could just add it all up at the section. Let's look at this geometrically of what's going on first, before we drive into the next part. So like, we're looking at this area right here. But f of x is negative there, so like area 1 is gonna give us a negative value. And we go area 2, like. There's no value here. There's no area. So this should give us a 0. For our area, because there's nothing underneath the curve. And from here, we're looking at this rectangle right here. This should be, it's above the f or the x-axis, it should be positive. Area 1, it has a height of -1. And the length is how long? This was -2, -3, -4, a length of 2. Maybe. Height is kind of like width here. Of our rectangle. So geometrically, length times width. Is gonna be -2. Area 2 should give us an area of 0. Because it has no area. And area 3. We have a height of 2. F of x equals 2 here. And we have a length of, we're going from 3 to 4 to 5. The length is 2 here. Also. So length times width should be 4. If we all add those all up, we should get 2. This is without looking at the intervals here, just looking at the geometric shapes. Is anyone not okay with this?
Where are you getting the -1, the 2, the 2 and the 2 from?
So I'm looking at a rectangle here.
Uh,
And I got length times width, so like length
Oh,
and
okay.
width,
That's how you're looking at it, okay.
yeah,
I just kept looking at it on like the x-axis. I was like, I get you're getting 2, but I was, okay, I wasn't realizing.
the width is really the height, and we gotta account for negatives. Cause we said that it does a net area. So like part of the red area is offsetting part of the green area. Shit like this shows up all the time in like economics. Like red is you spent money and green is you gain money kind of thing.
Spent 5,000, gained 7.
Yeah, or red is, we didn't make enough. Products that when we sell them, our net gain was 0 or under. But as soon as we start selling enough. We're back up to even. And then we start making a profit. So how does our intervals work here? Let's look at. adding in the interval part. So ignoring the boundaries or limits of integration, what would this integrate to? It's negative x, right? If I add an x to this, I still have 0x. So that's just still 0. But if it helps, put the 0x so you see it. And if I do this one, 2x. Now I know, like, this is representing area. This should lead to the -2 that we had up here for area 1. We can see that's already gonna be 0 no matter what, because we've got 0 as the answer. And this should lead to 4 for area 2, or area 3. The way we actually do this, it's one of the part, we'll go over in more detail on next week for 5.6. It's called the fundamental theorem of calculus. There's 2 parts to it. And this is in 5.6, we'll cover it in more detail later. And to be honest, I don't remember which part is which. I know what both of them are, but I don't remember like which one is 1 and which one is 2. The one that applies here is if the derivative of f of big X equals little f of x. Then if we're integrating f of x dx. This leads to f of b minus f of a. So integrate. Then plug in lower limit or upper limit minus lower limit.
Upper limit, b minus.
B. And the notation they do, with the way they show this. Is they'll say f of x. They put a long vertical bar. And they'll say a to b. That tells you like that's where you show your limits before you actually do the evaluation. So integrating this up here, we get negative x from -4 to -2. I'm actually going to show all 3 parts. Just to get you more familiar with it. So we're gonna do -2. That's negative x with -2 plugged in. This is my f of b. Minus f of a. Is -4 plugged in. Notice this gets us 2 minus 4. Which is -2, which was exactly what we wanted for the area of 1. I could do the same thing for the 0, but. We've got. 0 times 3 minus 0 times -2. Again, f of b minus f of a. Still 0. And in general, you would not write this all out, I'm just showing that it does work even when it's 0. If we do this one, I've got 2 times 5. That's my f of b. Minus my f of a is -2 times 3. This is 10 minus 6. My area is 4, and that was the area of 3. We will do that a lot more in 5.6, that's where we're going with this. But there are a lot of properties we want to cover in the next 10 minutes. Yeah, shall. Again, we will do a lot on this on Tuesday. So even though it doesn't look like we're hitting it a lot right now, we will hit it a lot on Tuesday. I'm just giving you a sneak preview of where we're going. So I'll rewrite that rule we had. And this, when we write down the following properties. You'll kind of see that it's true. So like. If we have we're going from A to B, f of x dx. This is exactly equal to if the order of integration is switched. Or the limits of integration are switched. Notice the left side would get me f of b minus f of a. And the right side gets me negative f of a minus f of b. But when I distribute the negative, I've got negative f of a plus f of b. Which is just that rewritten in a different order. So if we switch the limits of integration, we slap on a negative sign. Which is handy when you, like, if something happens and you get it backwards. So that's the first property to note. Property 1. Property 2. If you're integrating and your boundaries are the same, the lower limit is the upper limit. This equals 0. And you'll look at it, if we use the fundamental theorem we had up there, this turns into f of a minus f of a, and that's just 0. We don't even know need to know what the function is, it's the value at the same point, they're identical. Those two are kind of new and unique to definite intervals. The following we've seen before. For indefinite intervals, if we have some constant in here. We can just pull out the constant. We also saw this property on indefinite intervals. If we're going from A to B and we have f of x plus g of x. Dx. We can split this into two intervals. And the same is true if there's a minus, f of x minus g of x, it just turns that into a minus. So these are the, let's see. Is there another one that's the same as the indefinite? No, so these are same as indefinite. We just saw this property at work, if we go from A to B. Of f of x dx. And then we go from B to C of f of x dx. This is like doing from A to C f of x. Dx. Pictorially, that's like having A, B. And C. And adding area 1 to area 2 is the same thing as doing one big A. The following two are, in my mind, not that helpful. In terms of like applicable uses or uses you're gonna do like engineering shit. They are, I'm sure there are some examples where they pop up. One of them is called the max min inequality. If little m is less than or equal to f of x, which is less than or equal to big M. Like a min and a maximum. Then. Little m times b minus a. Is less than the integral. Which is less than big M times b minus a. Oh, that property 6. Where is like the application of this? Like if we look at the sine wave. Sine caps at 1 and -1. So like if I'm looking at it. The area should be between. Doing like if I go from A to B here, let's say this is A. And this is B. No, we'll choose somewhere in the middle, so it's like. Off. Then little m would be the -1. Like -1 times b minus a. Is less than or equal to the area. Which means this whole, like if we did this whole lower rectangle. This is -1. That rectangle is m times b minus a. And my big M is +1. B minus a. It's like saying this area is less. Than if we had the whole positive region. It just gives us a cap. So we know that we actually have an area and it's not infinity. And, like, if you're like, I don't know if that value looks right. Cause we get some weird answers with like decimals and shit, and you're like, that don't look right. Just picture the rectangle and do a rectangle over that region, you know it has a boundary. You can do a rectangle over the region, quickly calculate the area of a rectangle, that's just length times width. And you can go, oh, yeah, 2 times 5, which is a little over 6, is less than 10. So yeah, that is at least reasonable. Where it shows up. Not that often. The last one is called, this is a fun one called domination. If f of x is greater than or equal to g of x. For all x on AB. This is only a fun one because of the name. Then. The integral is greater as well. Or it could even like come down and. Maybe hit the edge, let's do that. Come down and hit the edge in the middle. Maybe that's F. Point is that this is the g of x. And f of x has that plus this. So it's more. And we'll call it a wrap, we'll do some more examples. Of this in the next section. Note. We don't have the plus C here. When you have limits of integration or a definite integral, you do not need to add the plus C.
Is that because it's not continuous?
No, it's because we actually have an n, and so we don't, the constant is known, we can find it. In fact, we're not even using it to have a general function, we are getting a value. By plugging in the limits. If you plug it in, if you have the plus C. When you do the f of b minus f of a, you're gonna have the c minus c, they go away. We'll show that again on Monday or Tuesday. Have a good weekend, I will be at the Mesa Center on Saturday, if you're wanting to come and get some practice. Come on in, otherwise I will see you Tuesday. And I will have your test on Tuesday. Rain or shine. Well. Why did I have that? It's
Unrelated to this, so I need to verify who's what's going on. So, look, so for, we're looking at, so here's the thing, so for computer science, we were doing a program that would make 50 random pentagons, with random sides and random radius. But I found, isn't that incorrect? Because at some point, the radius is way too big for a side, like too small, right?
You will need a relationship between the base and side.
So what I did was I found circumradius, that circumradius is based on the sides that it gave. So that's the proper way to do it, right? Because if you were to use like random numbers for everything, you're gonna end up with something that's not a proper.
Right.
Okay, just want to verify, because
Right.
I did that.
I would look up the relationship between radius.
Okay, because I did that, I'm pretty sure Mr. Redden at that point did the lab completely wrong and everybody got it wrong. Because the rule said, you have to make a pentagon. So the thing is that.
You wouldn't end up with actual pentagons.
Yeah, I found I got weird shapes completely when generating what's supposed to be pentagon.
Right,
Where I did pentagons that didn't even close, like that wouldn't even close, and I actually drew them out.
if you draw them out, it's not gonna work. I would more for the purpose of that lesson is to take from it. The procedures of how to do the programming, whether the pentagram worked right or not. The correct way to do it would be you make one of them random and calculate the other ones based on equations. Or point out to him that he was wrong. I always love pointing out to Red when he's wrong. In fact, I will point out to him that he was wrong.
No, I already did.
I won't quote you, I won't reference you.
No,
I'll just tell him he's
I
wrong.
already did.
Oh.
The thing is, I went to him and I said, I'm pretty sure that was a math error, because if he wanted to get the actual, like, the accurate, size pentagram, the actual pentagram works.
Right,
You need to, find a relation, find circumradius for all of it.
yeah, you would definitely need other stuff.